Now with the mathematical combination, the order does not matter. That's the key difference between the formula for a combination and a permutation. And so let's look at an example. Example number 4 says a class has 30 students. 5 are chosen to solve math problems on the board. How many different ways can the professor select those students? And it's very similar to the example above, where we had 30 students and we were electing a vice president, the president, and a treasurer. But notice in that case, it mattered. The first choice affected the second choice, where it's like the order mattered in which those were selected. Because if person A was selected for president and person B was selected for vice president, it's different than if person B was selected for president and person A was selected for vice president. So that gave us different situations and why the formula was a direct multiplication of those things. But in a case like this, it's going to be different because if I am, let's say I select 5 students, or even if we were to make the situation more similar to above, where let's just say 3 are selected to solve math problems on the board. Well, for our first choice of students, there's going to be 30 choices. But afterwards, we could there'd be 29 choices and 28 choices. When I'm selecting a group of students to work on the board, the order did not matter, because if I selected students A, B, and C, that's not a unique selection than if I were to select A, C, B, or if I were to select students C, B, A, or so on. So let's kind of look at that. Let me try to write out what I'm saying, because I feel like I'm doing a poor job expressing it verbally right now. But essentially, there would be 24,360 ways of permuting 3 choices from 30. Let's just say we were looking at what if there were 3 choices for groups. I was picking 3 students to do math on the board instead. Basically, there would be a lot of duplication, because in all of those groups, this would count for every single arrangement of those 3 student choices. And what I'm trying to say is whether we select students A, B, C to do work on the board, that's different than if we were to select A, C, B, or let's say we were to select students B, C, A, or B, A, C, or C, B, A, or C, A, B. Basically, in these 3 cases, if I was selecting president, vice president, and treasurer, these would all be different answers, and these are all included in this number for the number of permutations. However, if I was selecting 3 students to do math on the board, all 6 of these outcomes would be the same outcome, really, because those would consist of the same 3 students doing work on the board. So kind of how I like to think about it is, in a combination, there are less unique results, because technically there's 24,000 ways of permuting these 3 choices. But there's a lot of duplicated answers in that calculation, and the combination formula will compensate for that. So let's say we were going to apply, basically there would be 6 duplications in there, and the easy way to figure out, well, how many different groups of these, if order does not matter, would be you take this and divide by 6, and that would give you the simplified outcome. And that's kind of the idea of the formula to kind of get us started. So let's say we were going to use the combination formula to do this. Instead of being 30p3, this would be 30c3, or again, often written as c30, 3, depending on your textbook. And basically, let's go ahead and just use the formula and see how this all works out. Basically, we're going to have n factorial on top, which is the first number, 30 factorial, divided by n minus r factorial. Notice that this component is exactly the same as the formula for the permutation, which would leave us with 27 factorial, because n minus r is just the difference between those 2 numbers. And then notice there's one new thing in this formula. It's also divided by r factorial, which is the second number, 3 factorial. So in this case, basically what we're going to do is we're going to take the exact same ratio, which if we perform cancellation upon that, the 27 factorial would cancel, leaving us with 30 times, because 30 factorial is equal to 30 times 29 times 28 times 27 factorial. And the 27 factorials will cancel. And this would leave us with 30 times 29 times 28, notice divided by 6. And that's kind of what I was trying to say earlier, when I was explaining, well, if the order does not matter, these would all be the same answer. And so basically permutations count all of the arrangements. If we want to remove the duplication, we just divide it by all of those number of permutations of those objects, which in this case would have been, there would have been 6 ways to permute 3 objects. And here, notice that's all that this formula is doing. It's introducing a division by r factorial, which will cancel out those cases where the order, where we're counting order. And basically, this is just compensating for what if order does not matter in these cases. And basically, we just take that answer, divide it by 6, because 3 factorial, you know, is of course 3 times 2 times 1. So I'd have 30 times 29 times 28 over 6. And that would give me my number of outcomes. And actually, one other thing I forgot in the last video is you can actually, your calculator actually will typically have permutations and combinations stored within it. So let's say I wanted to do what if I have 30 objects and I wanted to figure out how many groups of 3 would there be. Basically, that would be starting with the combination formula, and it's in that same menu as the factorial. If you go into math probability, notice that you have both nPr and nCr. Let's go ahead and check our answer here to see if it's going to come up with what nCr would give you. And what you want to do is you want to start by typing in 30, then nCr 3. And this will be the same as 30 choose 3. A lot of people say this as 30 choose 3, or combination of 3 as just a shorthand, and that ends up giving 4,060. And notice that that should be consistent with, if you have your formula memorized, you can figure out the answer without a calculator. Or it should also kind of make sense. The whole goal in me going through all this in such an elaborate way is to try to make sense of the formula. Why does this answer work the way it does? But essentially, we have 3 things. There's 30 times 29 times 28 ways of doing it, and there's 6 duplications. And that's kind of the logic of why the combinations make sense. But notice, you know, it gives you the same thing, and you can use your calculator to do combinations if you just use nCr. And same goes for nPr. Let's just verify our calculation for 30p3, or 30 permute 3, people often say. If we do 30 math probability, again, that would be number 2, 3. That would give us this number, again, which matches what we got before. So long story short, your calculators typically will have these formulas for permutations and combinations in them. So what is more important is that you understand when to use these things. When do I use a combination? When do I use a permutation? And what I like to always recommend is that order matters. Or does order not matter? If the order in which I select them does matter, like in the case of selecting people for specific positions, or often the term arrangement or order will be used, then you want to use the permutation formula. If the order does not matter, like often a committee or a group or something like that, those sorts of terms will often be used with a combination problem, then you want to use a different formula. In that case, the order in which the group, whoops, about my mic, the order in which the groups are selected does not matter. Like in this case, if I'm like looking at this problem once again, here, let's actually solve the problem as it was originally stated in the lecture notes. Here we have 30 students and 5 are chosen to do math on the board. And again, the order in which I select those students doesn't matter, because whether student A is selected to do math first. Now, the order could matter if they're all solving different problems. Then the order I select them would matter. That would be a permutation. But here, if they're all solving the same problem, it doesn't matter the order they're selected, if you catch my drift. And so this would be 30C5, or again, that would be equal to C parenthesis 30 comma 5, depending on your textbook. And again, that would amount to be 30 factorial divided by the difference factorial times r factorial. And you could simplify that, or you could even just type it in as NC, like 30C5, or you could even just use factorials. There's quite a few different ways you could come up with the answer here, but I could always do 30 factorial, and this is probably the most, annoying way to do it, divided by, make sure you're using parentheses for the denominator if you're going to do it the way I'm doing it right here, with the exclamation points, but it would be 30 factorial divided by 25 times 5 factorial, and apparently there will be 142,000 ways to select students to do, a pretty staggering number. But you can see, like, if we were trying to figure these things out without a formula, how difficult it would be. that's kind of the point of having these formulas as such. Or again, we could use this probability feature and do nCr 30 choose 5 is how a lot of people will say this. And it amounts to be the same thing as well. And one last thing is actually another way that combinations are written in a mathematical sense is by using a kind of a weird notation. But basically, if you put like a parenthesis with two things within it, it's kind of like a larger parenthesis, sort of looks like a matrix. This is often what's referenced as a combination notation. So if you ever see like in a mathematical equation like 2 plus 3x minus and then 3, 2, it's kind of, it would appear in the mathematical statement in a parentheses with two numbers on top of each other. This is always a shorthand for a mathematical combination of, you know, in the same exact way I would say before. So it's just a different way of writing it, used for in the binomial theorem and a few other things. But that will wrap up our talk on this for this semester, because, you know, this is enough for the last week of class to get into. But anyways, it's been a great semester. Thanks for all your hard work. And yeah, hopefully you should be good to go for the remaining homework problems from chapter 10.